Hi everyone, here is a solution for challenge problem 3. My team members are Vicky, myself, Renuka and Gustavo. The given question is, I have in my pocket M fair and N two-headed coins. I withdraw one coin and flip it k times. Let H be the event of getting a head and EK is the probability that all k tosses of the chosen coin is heads. Let F be the event that the coin is one of the fair coins. Our task is to analyze the conditional probability of selecting a fair coin given that we get heads in all the k tosses and to calculate the smallest m and n values to satisfy the given four conditions, which are probability of f given E2 is equal to 1 by 5, probability of f given H1 is equal to 1 by 2, probability of f given E2 is equals to 1 by 2, probability of f given E3 is equal to 1 by 6. Before working on the solution, we will discuss the conditional probability in more detail. What is conditional probability? It is the measure of the probability of one event given that another event has occurred. P of A by B is read as probability of event A occurring given B has occurred, which can be explained with the help of a tree diagram. Let P of A be the probability that event A has occurred and P of A complement is the probability that event A has not occurred. Now we limit ourselves to the probability that A has occurred. Given A has occurred, either event B has occurred or has not occurred, which is what we see in the two sub-branches. Similarly, for the case that event A has not occurred, we again have the case where B has occurred and B has not occurred, giving us the remaining two sub-branches. In order to calculate the probability of one branch, which is nothing but the product of the individual sub-branches, which is shown below. Probability of A given B is nothing but probability of A intersection B by probability of B, which can be written using Bayes' theorem as probability of A multiplied with probability of B given A by probability of B. By using law of total probability of B can be written with the help of the tree diagram as shown here. We have probability of B we'll get probability of B either by event A has occurred or A has not occurred, which is sum of these two equations. So, which is nothing but probability of A given A intersection B by probability of B given A multiplied with probability of A plus probability of B given A has not occurred multiplied with probability of B.
We go back to the original question. We have M fair coins, which we denote by F, and N two-headed coins, which is denoted by 2H, or simply F complement. The total number of coins will be M plus N. We randomly pick one coin of the total, as can be seen in the tree diagram. The probability of choosing the fair coin will be M divided by the total number of coins, and the probability of choosing a two-headed coin is N divided by the total number of coins. In the case that a fair coin is chosen, we have the equal probability of flipping tails or heads, which is 0.5. In the case that a two-headed coin is chosen, we will always flip heads. As we continue with k flips of the same coin, we can see the tree diagram expanding. In the case of the unfair coin, we will always end up with heads. Applying Bayes' theorem, which we saw in the previous slide, we get that the probability of getting a fair coin given that we get heads on k flips is equal to the probability of getting heads on k flips given that a fair coin is chosen, times the probability of choosing a fair coin divided by the probability of getting heads on k flips. The probability of getting heads on k flips, given that we have a fair coin, will be 0.5 to the power k, times the probability of choosing the fair coin, which is equal to the number of fair coins, which is m divided by the total number of coins, m plus n. We divided all by the total probability of getting heads on k flips, which is the sum of getting heads given a fair coin plus getting heads given the two-headed coin, as shown in the equation in the bottom part of the equation. We simplify this equation to get m times 0.5 to the k divided by m times 0.5 to the k plus n.
Okay, so now that we have the expression for calculating the probability of f given E sub k, we can use it to find the smallest value of m, which is the number of fair coins, and n, which is the number of two-headed coins, for satisfying the following conditions. For the first case, we need the probability of choosing a fair coin, given we got two heads in two trials, to be equal to 1 by 5. If we use the expression from above, we can plug in the value k equals to 2. Further simplifying the equation would give us the ratio of m by n is equal to 1 by 1. Since this is a reduced ratio, which means you can't reduce it anymore, the number of fair and two-headed coins should be 1 each in this case. Similarly, for the second case, we find that we get a ratio of m by n is equal to 2 by 1, which means the number of fair coins should be 2 and the number of two-headed coins should be 1. Same for the third case, where we end up getting a ratio of m by n is equal to 4 by 1. And lastly, for the case where we need 1/6, we get m by n is equal to 8 over 5, which means that we need a minimum of 8 fair coins and 5 two-headed coins to get the conditional probability to be equal to 1/6. And those are our final answers. Thank you very much.